Hello, everyone. I'm going to talk about why many mechanisms are not much better than item pricing. This is joint work with Shuchi, Chawla, and Christos, Tzamos. So we consider a setting where a seller would like to sell n items to a single buyer. The buyer has private value function defined for every set of item. And the value function is unknown to the seller, but the seller knows the distribution of the valuation function, for example, by studying the historical market data. And the objective of the seller is to maximize the total revenue. So let's start with an example in this setting. Suppose that a seller would like to sell a sandwich and a drink to a single additive buyer. The buyer has value 1 or 3 randomly for the sandwich and 1, 2 randomly for the drink. So it is known that any single buyer mechanism can be represented as a menu of choices. For example, the optimal mechanism in this setting has 2 menu entries. The buyer can either pay 4 and get both sandwich and drink, or pay 2.5 and get the drink for sure, then toss a coin. If it is a head, then she also gets a sandwich. So it is known that the optimal mechanism for multi-item setting can be very complicated, has many unnatural properties, which make it hard to analyze or compute. So the same as in Minfei's talk, we would like to approximate the optimum revenue by simple mechanisms. So let's start with some notations. Let opt denote the optimum revenue obtained by any randomized mechanism, and drev denote the optimal revenue obtained by a deterministic mechanism. Srev denote the optimal revenue obtained by item pricing, which price deterministic price to each item. And Brev denotes the optimal revenue obtained by pricing the entire bundle. So there are a lot of previous results working on getting small gaps using a simple mechanism, for example, grand bound pricing or item pricing. But the previous results mostly rely on the fact that we know the structure of the valuation function, for example, subadditivity. And we need to have the independence over the value of the items. On the other hand, we actually know that for multi-item setting, if you do not have the independence assumption, then the revenue gap between the optimal randomized mechanism and deterministic mechanism can be infinite, even for additive or unit demand buyers. And the revenue gap between optimal deterministic mechanism and item pricing can be exponential in n for additive buyers. So is it really impossible for us to get positive results for general value buyers? So actually, we have the following observation, that the typical menu in the previous large gap examples usually overcharge for a bundle while selling individual items at much lower prices. In the classical setting, the buyer is only allowed to purchase 1 menu entry from the menu. For example, if a restaurant has this menu and I would like to buy a sandwich and a drink, I may buy the second menu entry and the third menu entry with price 3 rather than 4 and come to the restaurant twice if I really need to do. So this means that if the buyer is allowed to purchase multiple menu entry, the first menu entry is actually redundant. And the main question studied in our paper is that how will the previous gap change when the buyer is allowed to purchase multiple menu options? So let's define the class of mechanism we studied, that is the Sybil proof or by many mechanism. In security, Sybil attack means that the attacker creates multiple false identities to gain huge influence. And similarly, in mechanism design problem, we say a Sybil proof or by many mechanism to be a mechanism that allows the buyer to purchase any multi-set of menu options at the sum of their prices. The buyer will obtain an independent draw from each option and get their union. For deterministic Sybil proof mechanism, it is simply equivalent to monotone subadditive pricing. So we want to ask, is the optimal revenue of Sybil proof mechanism still infinitely better than simple mechanisms? The answer is actually no. And now we propose our main results. Our first main theorem is that for arbitrary distribution over arbitrary valuation function, item pricing is O log n approximation to the optimal stable proof mechanism. This works for arbitrary valuation function with correlation and do not need subadditivity. This improves the previous result for unit demand buyer. So we have a O log n gap, so can we do better? Actually, we proved that this O log n gap is tight, that there even exists distribution over additive valuation function such that no succinct mechanism can get small O log n approximation to the revenue. Here, succinct means the mechanism that can be described by sub-exponential number of bits. So on the contrary, to get O log n approximation, we only need to use item pricing that only needs to use a linear, almost linear number of bits. So we may observe that the stable proofness really has a huge constraint over the optimal mechanism. That without such assumption, the revenue gap between item pricing and optimal mechanism is infinite, and now it is only theta log n. And we also observe that most simple mechanisms we have studied before, for example, partition pricing or a max of item pricing and bundle pricing, will still have the omega log n gap. So now I will briefly prove the two theorems, and let's start with the upper bound results. For simplicity, in this talk, we prove that item pricing is O log n approximation to the optimal deterministic stable proof mechanism, which is simply monotone subadditive pricing. To prove this theorem, we first prove this following lemma that is interesting on its own. Informally speaking, it says that in order to get O log C approximation in revenue, you only need O of C approximation pointwise. In particular, I'll give two pricing functions P and Q such that for every set S, Q pointwise C approximates S. Then for any value distribution D, there exists a scaling factor alpha such that the revenue of Q scaled down by alpha is O log C approximation to the revenue of P. Such lemma also extend to the pricing functions over randomized allocations, which can be used to prove more general theorems. So then theorem 1 follows easily given lemma 3, that you can set the pricing function P to be the optimal subadditive pricing and let pricing function Q to be the item pricing that sets price Q P of I for each item I. Then, on one hand, for each set S, P of S is upper bounded by the sum of item prices inside S, which is exactly Q of S. On the other hand, it is lower bounded by the maximum item price inside S, that is at least Q of S over N. So the pointwise approximation, C approximation, holds for C equals to N. Then theorem 1 follows after lemma 3. So we only need to prove lemma 3. And we actually prove a slightly stronger result saying that for two pricing functions P and Q such that QC approximates P pointwise, there exists distribution over scaling factor alpha such that for every possible valuation function V, the revenue of our Q is in expectation O log C approximation to the revenue of P. Then lemma 3 follows immediately by taking expectation over all valuation function V. So on the face, it may seem like a simple scaling argument will work, that if the buyer purchased set S star under pricing P, then there exists a scaling factor being power of 2 between 1 and 2C and 1 such that alpha times QS star is between half of PS star and PS star. So if buyer V still purchases set S star under pricing alpha times Q, then we actually get 2 approximation because the revenue will be at least half of PS star. And since there are only O log C scales, then we get O log C approximation. However, the main problem is that under a pricing function alpha times q, the buyer can deviate to purchase some other set S prime that has a much smaller revenue, a much smaller price, but she may get a larger utility. So this means that the revenue bound in the previous analysis will not work. However, we actually may expect that in this case, the utility of the buyer is actually large. So we may increase alpha or increase the price to get a more revenue by reducing the utility. So let's see what happens when the scaling factor alpha increases from 1 or 2c to 1 and observe the utility curve and the revenue curve as a function of alpha. So if there is only one set S1 sold on the menu, then the utility will decrease linearly with respect to alpha, and the revenue will increase linearly at the same time, and the decrease in utility is actually captured exactly by the increase in revenue. When alpha increases, the buyer may deviate to purchase other sets. And the utility function would be like a piecewise linear function, and in each segment, it corresponds to a particular set purchased by the buyer. And at the same time, the revenue would also be a piecewise linear function, but it will drop abruptly at the breaking points. But the good observation is that the revenue is actually a piecewise linear function, and the gradient of the revenue is proportional to revenue itself. So we can observe that the derivative of the utility is actually a negative derivative of the revenue, which is exactly negative revenue over alpha. So we want to bound the expected revenue. It will be proportional to the expected gradient of revenue if we choose alpha to have density function proportional to 1 over alpha. And the expected gradient of alpha is exactly the utility loss at both endpoints. So to summarize, we observe that under such a distribution of alpha, the expected revenue is O log C fraction of the utility drop at both endpoints. So it only remains to prove that the utility loss between both endpoints is large. So we can observe that when alpha is large, then the price is actually greater than price P, so the utility is smaller. On the other hand, when alpha is small, we actually give huge discount to the buyer, and the discount is actually can be lower bounded by half of the revenue. So we can conclude that under such distribution of alpha, the expected revenue is O log C approximation to the revenue of P. So this finished the proof of this lemma. Now we show how to prove the lower bound. In this talk, we will prove the lower bound for the single-minded buyers. And the key observation is that there exists exponential number of sets such that the price of each set can be defined to be arbitrary value within 1 n poly n, and it can still be completed to a subadditive function. So we can have a single-minded value distribution as follows, that with probability 1 over big N, the buyer demands set Si with value Bi. The idea is that the optimal pricing function is defined by value on exponential number of sets. In the previous proof, the value for each set is bounded in the range of poly n. So we can guess the correct scale and get O log n approximation without further information. However, if we want to extract a more than O log n fraction of the revenue from any set, we need at least 1 bit to store the information for the scale for the set. Since there are exponential number of sets, thus a mechanism that gives small O log n approximation must be described by exponential number of bits. So now I would like to conclude my talk. We proved that by-many mechanisms are not infinitely better than item pricing. This means that stable proofness significantly restricts the seller and lowers the revenue by unboundedly large factor. So for an open problem, it would be interesting to revisit some classical results working on optimal revenue under the stable proof assumption. For example, can we get better approximation for the special case, such as independent items and additive valuation? What would be the manual complexity for 1 minus epsilon approximation? And would additive buyers have revenue monotonicity under the stable proof assumption? So I will stop here and take the questions.
I have a question. When you define stable proofness,
okay.
You're taking independent draws for the different purchases,
right?
But if I was really worried about somebody purchasing multiple times over false identities, it seems like one way to combat that would be to correlate the draws.
So we may have the adaptive stable proofness saying that you have the stable proof, so you will decide whether to come again given what you have bought in the previous draw. So adaptive stable proofness is actually a weaker constraint of the non-adaptive stable proofness, and actually our result holds for both cases. Okay. Hi, Nick.
So this kind of relation between item pricing and stable, like by many mechanisms, is not constructed. So basically, you say that there exists pricing that is kind of good approximation to by many mechanisms. Is there any kind of way to construct such pricing?
So actually, so it says that there exists some, there exists distribution of alpha. So you can randomly choose an alpha, follow the, follow that distribution.
You can actually get like good approximation explicitly.
Yeah, explicitly. But you need to have the optimal stable proof pricing, and finding that is hard actually.